Rolling. Thank you everybody for coming up this afternoon. Hope you're enjoying the conference so far. So this afternoon we're going to speak for a few minutes about easy scalability with Akka. I purposely put the word easy in there because I think this is a straightforward technique. It's a pattern that we've applied a few times at client sites. So first of all, who am I? I'm from Bold Radius Solutions. That's our URL. We're a type-safe partner. We've been around a long time. We do Scala, Akka, and Play. And we enable companies to adopt the platform. So often we help people get started or help them over some of the more difficult bits of getting used to the type-safe reactive platform. We have offices all over North America primarily. Most of our people are in Canada, but we have a few people in the States, and we do visit Europe quite a bit. I'm Michael Nash. I'm our VP of Capabilities. That's my Twitter handle. That's my email. So, what do I want to talk about? What are you going to know in the next 45 minutes that you didn't know when you started, perhaps? I'm going to talk a little bit about a technique that's been called distributed domain-driven design. What it is, how it applies to a project, some fancy acronyms, CQRS and ES, and how do they relate? How does all of this tie to Akka? And how do you do distributed domain-driven design with Akka? What's different? Looking at a project that's not using these techniques, looking at a project that is, what do you actually do that's different and how impactful is it? And what does it do to your scalability? How does that scale compared to a normal Akka project that doesn't necessarily use these patterns? Okay, so just to set some terms, it's important to understand that scalability is not performance. They're related, but not even directly. Performance increasing means your response time is reducing. You're getting replies faster, potentially, if you're doing it right. Scalability increasing means our capacity improves in relation to adding resources. So we put more something, more servers, more CPUs, more nodes, and we have the ability to handle a higher level of load. So they're related, but subtly different. So scalability, you've probably heard this already. Scalability can be that we scale up, e.g. a bigger box or more boxes, more CPUs in a single server, or we scale out, more nodes. Both are valid, both work. Often we talk mostly about scaling out simply because you can only get boxes so big in most environments. You can only afford boxes that are so big. So Akka, this again is probably old hat for most of you based on the last couple of days. But essentially Akka is an implementation of the actor model, which predates Akka by a long time, for the JVM. Share nothing distributed message-driven compute model is the technical term for it. There are, of course, Scala and Java APIs. If you've ever worked with Erlang or Elixir, a little bit like Erlang or Elixir processes, only I think better in many ways. And again, many people over the last couple of days have been explaining that. What they haven't necessarily been explaining is terms like CQRS and ES. CQRS is commonly termed Command Query Responsibility Segregation, which is a mouthful. We'll talk about it in detail more and see that it's actually a very simple approach. Event sourcing is actually even simpler and is often used in combination. Event sourcing is state built from a journal of events, specifically events, not commands. There's a difference. One doesn't need the other. You can have CQRS without ES, you can have ES without CQRS. Often you see them together and they work well together, but they're not a prerequisite one for the other. So in very simple terms, event sourcing, the way I'm defining it for here, is a series of events stored into a journal. That screen is catching up, right? Okay, good. And that journal being read by some domain instance. And again, I'll talk more about what I mean by that. In a very quick nutshell, that's event sourcing. CQRS is a little different. CQRS is a series of commands. It's the separation of the read and the write side of a problem, and typically separation of the implementations of a read and a write side. So a series of commands being written, perhaps to a journal, per some manner of queue, that are being absorbed by a write model. That write model then produces events. Now, as you can see, one flows nicely into the other because those events can then be consumed by a domain instance that's doing event sourcing. So that's how the two can gel together very simply. So domain, I keep throwing around this word. Do I know what it means? Your application's domain, in plain English, is the part that relates to the problem. It's the problem, not the plumbing, I often call it. The rest of your application is infrastructure. It's the code you have to write that supports the stuff that solves the problem. So if you're writing a payroll application, then things like employees, benefits, pay stubs, and the operations associated with those things are part of the domain. Reading and writing into a database is not part of your domain. That may be how you accomplish your domain, but it's not the domain itself. So domain-driven design, which many of you may know the term of, is not only for object-oriented systems. It's a design approach that talks about the domain and the infrastructure as two separate elements, and it has a lot of other terms, and we could talk about DDD for an entire 45 minutes. We won't. Object-oriented and functional, just like object-oriented and functional are not an either-or choice, as Scala shows us. They're actually very synergistic. The same thing is true about being distributed and domain-driven design. For a long time, it was thought, domain-driven design, that's not really applicable to functional languages, only really works in a single system. None of that is really true. It works just fine in a distributed system. We've used it, it works. Distributed domain-driven design is actually a really good fit with the actor model, and you'll see why I think that in a minute. So what do I mean by a traditional domain instance? A traditional domain instance is what we have all probably done for years in our applications before the advent of things like Akka and Scala. And that is you have a domain object instance, say a customer, and you send reads and writes to methods on perhaps some object that manipulates that domain instance, and you probably write its state as a full snapshot of all of its state in and out of a database. Right? That's the way we've built applications for a long time. Works pretty good. So a non-distributed domain, to use a different term to think about it, is basic CRUD. It's your create, read, update, delete operations. Writes and reads to the same database. It's always consistent, has that benefit. The writes go to the same place the reads. So after you've written, you can read, you'll get the latest and greatest state out of that database every time. Typically it's scaled, so for situations where we need to handle a lot of requests over a short period of time, that's scaled via multiple identical replicas. We just clone the whole thing. We say, I need another one, another one, another one, another one. They all sit alongside each other. They all communicate usually with either the same database or replicas of the database. So this, again, is a pattern we've all probably used. There are bottlenecks in that pattern. You bottleneck on contention. Contention is your big enemy in trying to scale that pattern, often. Reads and writes can interfere with each other. Some databases are better at this than others. But it is, to a degree, the database engine's job to try to reduce that contention for you. What I'm going to propose as a pattern is a way to do that from an application level. So when we scale the traditional model, as I was just saying, you just clone the thing. You say, give me more of those instances, connect them together. Maybe you have some means of sharing in-memory state between them. But you can think of that logically like a database again. It just happens to be an in-memory database. Each instance must read that state every time for consistency. So if I want to know what the balance on that customer is, let's say, I've got to go read the customer from the database. I can't trust the copy that I might still have in memory or in a cache necessarily, particularly in a distributed environment under high load. It could change very quickly. Each must write fully to that same shared resource. So when I say fully, I mean you can't do it asynchronously. You have to write, hang on, okay, I've written, great. Now we have consistent state for the next guy to read, in case the next operation happens to affect that exact state. So scalability has some limits in this environment. It kind of looks like this when we deploy it. There's typically some manner of load balancer. Let's assume this is an HTTP web service. So we have a load balancer spreading different requests across our various instances, in this case only 3 of them. Might be 30, might be 300 of these. There may or may not be a cache involved, but the picture doesn't change that much if it is. And then we have these transient domain instances that we create, pull from the database to get data, do something with, and then essentially discard and garbage collect again. They don't necessarily last, so that's hence I'm using the term transient. And we have that central database. Now that database itself may be distributed or replicated, but logically there's one of them, not many of them. So, wouldn't it be easier and faster if we could just keep all your domain instances in memory? Have everything memory resonant? That's great. What happens when the lights go out, of course, is the eternal question. How to recover from the volatile nature, to be more technical about it. Well, an event journal might start to answer that question. And that's the beginnings of the pattern that I want to describe. So instead of necessarily the pattern that we just had in the previous diagram, we have something that starts to look like this, and we'll flesh this out a little more. You have, again, your HTTP API, probably with a load balancer in front of it. But in this case, you might be able to use Akka's cluster sharding mechanism and have non-transient domain instances. Again, I'll explain further what I mean. Let's say we had 15 customers. Well, we could divide up an instance, an actor, a piece of state in memory amongst our 3 nodes and route all requests for anything to do with transactions for customer 7 to the second node, for instance. Each of those nodes could have a separate journal to record its state, to record all of the events by which we could reproduce the state specifically. That's the event sourcing part. You notice now there's no lines between the boxes on the bottom of the diagram. That's a promise in the direction of that high scalability and flexibility we were talking about. But we have more than 15 customers, as hopefully most of us do. What do you do about that? I can't just put the whole database in memory. Well, pagination is how we used to put things that are too large for memory into memory, and Akka provides a mechanism that is very similar to that, in the sense that you can have active instances and passivated instances. A passivated instance is essentially a virtual instance. It doesn't actually exist in memory. There's no object, but it could be there if we required it, and it could be there quickly. So activation and passivation help solve that problem of how do I have all of my instances in memory. The actual response to that is you only have your active instances in memory. You don't have all of your instances in memory. And you don't even necessarily have all your active instances in memory, but we'll come back to that. So basically the sort of flowchart, yes, going back a few years, flowchart, of activation and passivation is that if I receive a message, if I'm an actor and I receive a message and I don't exist yet, which sounds a little peculiar, but the mechanism of Akka takes care of this for you, then of course I must activate, I must restore my state, if any, that's the event sourcing part coming into play, then I can process the message. Now I sit there waiting for another message. I sit for a while and I receive an idle timeout message, let's say. That's one way to passivate, is to say, you've been sitting around for 15, 30 seconds, 5 minutes, whatever the correct tuning is. No more messages for customer 605. Great, customer 605 is out of memory. So virtually, it still exists. We can still route things to customer 605, but he's not actually taking up any memory. He'll be restored via that mechanism if we need him again. So what happens if we put all of this in a pot and cook it? And if we say, what are the ingredients for an application that would actually do this pattern, and what would it look like? So some of the ingredients are Akka, of course, with the Scala API, with the clustering and persistence modules. Turns out we need those to do this. The database that we used, I guess you have guessed, I'm leading up to the fact that we've tried this, and we have an example application to be able to show you. The database we've used for this is Cassandra. Cassandra's pretty high performance all by itself, and even the CRUD model scales remarkably well with Cassandra. But we wanted to keep the variable small, and we used an Activator template, which I'll show you the URL for. And we've actually applied this in customer sites, but then we decided, okay, let's do an abstract one of these to be able to share it with other people. So what's different? Compared to the first time we wrote this application and we used the standard CRUD model, the key elements that differ are actually very small, which is why I feel it's okay for me to use the word easy in the description of this talk. It wasn't actually that far a leap, and yet in a certain sense we turned the design upside down. What we mean is the domain instances are transient, as we talked about, and they're memory resident when they're in use. Even their state is memory resident when in use. Reads and writes don't contend. There's never a situation where I need to both change and read the state of a single customer simultaneously. That's, of course, what Akka brings to the table, the ability to queue those messages. And the cluster, there is a limit to this design, and the clusters can be grown until your number of domain instances per node equals 1. And I'll describe what I mean by that and where that limit is, and we'll see it on a graph when we look at some actual code. So what does this buy us if we were to do this? If we go through all this work, compared to the CRUD model, what do you get? What's the reward for doing this design? Well, the promised reward, and I hope to be able to prove it to you, is scalability. The ability to increase resources and therefore handle a higher load without hitting that curve that starts to reduce the effectiveness of additional resources, where your cost effectiveness starts to go down, or at least pushing that curve a long way away, as opposed to having it happen fairly soon. Failover. You also get, not exactly for free, but by using the tools in place, the ability to have no single point of failure or contention. You're actually eliminating that within your entire system, which by itself is a good goal. If you were trying to achieve just high availability, that would be an interesting way to do it. Instances can be created anywhere, as needed, anywhere within the cluster, of course, as needed. So you have elasticity as well, which I don't talk about here. And you have a certain amount of simplicity in the sense that it's very easy to build this app small and then not get caught short by success. You want to build for success, but you don't want success to be your biggest problem. That all of a sudden scale starts to exceed your capacity, customers get unhappy, response times go up. That's failing by succeeding, and that's a terrible way to go. Customers often call us somewhere on that curve, where all of a sudden they're going, this is working so well, now we're in trouble. And they'll say, hey, we need this problem solved. So this is a good moment to, before we dive into some code, think about your own domain. And one of the tricks to apply this pattern to your own domain is, can I in fact separate my reads from my writes? And oftentimes people go, no, they're all the same. They're combined. And that takes some thinking and some chewing. Oftentimes with a customer, we'll have this discussion and we'll sit at a whiteboard for a while and we'll start to realize that saving, storing, writing of data, the write operations in their model, are actually only somewhat related to the read operations of their model when you actually factor it out. So surprisingly, we come up with the fact that that's not always the same even now, even though typically we will combine those in a single class or a single operation. Deployment structure is critical to get all the benefits of this safely. It's very easy to mistune this model and end up going, it doesn't work. And we did that a few times, trying to come up with this presentation. So let's talk about some code. Let's look at an actual example application. Let's say we take online auctions, the eBay sort of model, much simpler. And let's build two implementations, is what we said. We actually had two separate teams that didn't really talk to each other. And we said, okay, let's build these two implementations, but have them implement the same design, which is users can place bids for an online auction to purchase some item. Simple enough. The vast majority of the code is shared. There's actually only a few hundred lines of code that's different between these two repositories. So the design is not, this pattern is not all-encompassing. It doesn't affect that much of your actual design. They have identical APIs. It's a REST API in this case, because that's easy to test and easy to show. They, more importantly, have identical deploy structure. We actually did this experiment on AWS, and we used the exact same machines, virtual machines. We didn't make other virtual machines. We just ran the code on the same set of machines. Although we were able to add more machines in one of the examples. Excuse me. And we start with the same number of nodes. One running CRUD, one running CQRS DDD. So the CRUD actor is Akka. It's actually Akka-based, so we didn't even introduce Akka for the pattern. We just used Akka a different way for the pattern. It receives requests, and it writes directly to the Cassandra cluster, writes straight to the data store. So every time someone makes a bid, we say, okay, there was a bid, the current bid is now such, and the object that we're saving is the state of that auction. So I'm not expecting you to be able to read that code. It's a little blurry in VGA. To give you an idea of the size of the code, that's the actor for the CRUD model. And we made no attempt to make that as short as possible. You know what Scala is like. You can start compressing code and making it shorter and shorter and end up with a very small piece of code. We wrote this fairly quickly and didn't compress it a great deal. So it's a page of code, let's call it. And this is the one that writes directly to Cassandra. And we're using the data stacks driver, as I said. So what's different on the other side? That's the core, that's the guts of our little CRUD application. That's the center of it. The rest is a little bit of REST API. We use Spray and kept it very thin. So the CQRS DDD actor, like I said, uses in-memory state. It recovers that state from a journal as the actor is started. So for a particular auction, that particular auction has this event journal sitting in Cassandra that it rereads on startup. It uses become, the become mechanism, to change its behavior, to change states. So it's in effect a very simple finite state machine. And it passivates on timeout. Passivate essentially means I'm now subject to garbage collection, I could go away. Now the code for that is a little bit longer, but not much. That's most of it. It's another little bit and that little bit. So 2¼ pages, something like that. One of the reasons I'm happy flashing past this code quickly is I'm going to give you a URL with all the code on it anyway. So if you want to dig into it in detail, it's quite readable, and it's short enough that you can actually just put them alongside each other and see the difference. But it's, what does that say, 177 lines of code. I think the last one was 100, somewhere in that pattern. So a little bit more code. And mostly the more code is because there has to be a mechanism to handle the persistence of that actor. So as as new messages are received by the actor, we use Akka Persistence to store them into an event journal after their effect has been noted. Sorry, the other way around. Their effect is noted after they're stored into a journal. Most important. Or it doesn't work. So what's our test setup? Let's actually look at some performance numbers. Our test setup, we started, so the minimal instance is 3 Cassandra nodes clustered, 3 Akka processing nodes, that is backend nodes, and 1 front end, which was running Spray in this case. We tried it with Akka HTTP. It was a little too early for Akka HTTP at the time. We wanted higher scale than it could do at the time. All of them were on what they call small AWS instances, so there's no serious compute power involved here. We used Gatling. You'll see the stress test tools icon up in the corner there, which just allows you to fire a great many HTTP requests at your application and then get pretty graphs of the results. We use that to simulate 100 simultaneous users, 100 auctions, and run for 2 minutes. Right? Very simple test, very short test. This is the simulation code. This is also in that repository. And all of the magic is actually down here on this line. The rest is mostly preamble and HTTP headers. There's actually an API with Gatling and a tool with it that allows you to interactively do your test, and it will record the actions and then play them back at volume for many users across many machines if you want. So what this says, because it's a little hard to read from the back there, is that I want to start immediately. After 4 seconds, I'm going to come up to 100 users, and I'm going to run for 2 minutes. And I'm just going to resend these HTTP protocols and then measure all of the responses. The kinds of things you get out of Gatling look like this. Here I've clipped out the individual graphs, so you don't just see one big page of graphs, but it all comes in a single pretty HTML file at the end. The CRUD application, the CRUD version of this code, is running on the left, and what we're looking at is response time distribution. So how many of our requests came back within what kind of response time? And what's interesting is you can see already that there's a very different shape to the response. Now they're on different scale as well. I'm not sure if you can read the numbers from back there, but the top of this scale is around 22, 23 milliseconds, something like that. Whereas this one is, milliseconds. The percentage of requests, 22, 23, came back within this percentage, within this number of milliseconds, which the bottom one here is 8. Over here, the bottom one is 11, and the percentage is something like 14. So a lot more of our requests started coming back a lot faster right away. Now, if you remember, the definition that I gave at the beginning of the talk separated the idea of performance and scalability. And I'm really only talking about one of those so far, but we'll get back to it. Response time percentiles are also interesting. Again, not so much for their numbers per se, they're on slightly different scales, but on the shape of those numbers. It's the response characteristics of a system using this technique that I want you to be able to see here. For example, this is the CRUD version. You can see it's fairly consistent. There's a little spike at startup, and then there was another little glitch there somewhere where some buffer flushed or something that happened in the Cassandra cluster, and you can see things got a little slower, but relatively constant over the 2-minute cycle. The CQRS one, though, looks very different. It's much more consistent in terms of its ability to respond within a specific number of milliseconds. The scale is much different in the sense that the number of requests we served, or the time that it took to serve requests went down after initial startup. Well, this is exactly what you'd expect to see. We're activating all of those instances. They're reading their journal, even if there's nothing in the journal yet. They have to go to the database to read the journal. So there's a delay as each of these instances become available. And then, of course, once they're in memory, response time is very fast. We're essentially dealing with an in-memory database, and write is the only thing that we're spending time on. And we're writing to independent journals. So as you can see, the points of contention are going way down here. We're trying to eliminate them. And this is the effect you get on performance so far, not so much scalability. The requests per second, Again, I don't know if you can read the numbers, but the top of this scale is 1,000. The number of, let's see, yeah, that's the number of requests handled over the 2-minute span. And so somewhere in the vicinity of probably 800 requests per second was the max that we were getting out of this cluster with the CRUD version. For the CQRS version, again, the shape of the graph is very different. We don't get the same response characteristics, and the scale is different. In this case, we got almost up to 3,000 requests per second on that same cluster. So even without any additional resources, we already have a much faster, we have a much higher ability to handle load, not necessarily faster, because that wasn't what we were going for directly. So let me sum it all up. Within that 2-minute span, the CRUD version of this application, about 100 lines different than the CQRS version, handled 75,900 and something requests successfully. The CQRS version handled almost 200,000 in that same period on exactly the same hardware. So the pattern certainly gives you an increase in load handling on a fixed set of hardware. Of course, it gets much more interesting when you then try to scale that picture. So what happens when we throw more hardware at this problem? We say, okay, don't change any code, change a little configuration, and start spreading this out across many nodes. The CRUD version, contention, of course, increases. So we're now competing over that database, and we're competing over that element of the database. Now, Cassandra does a lot internally to try to help us with that, but there is still contention. There's still a synchronization problem at a certain point of scale. It would be much faster, the contention problem would rear its head much faster with databases that aren't as good at doing this. So internally, Cassandra is using some of these techniques or techniques like it to try to help you overcome the problem. You end up with diminishing benefit for adding more nodes eventually. And where eventually is, I've got some graphs coming up that will show you where eventually falls on this. And tuning didn't help that much. We tried tuning, we said, okay, you know, let's play with the thread pool, let's play with the cage sizes. We got a little faster, got a little better. Because the goal was to say, if we take these two and we tune them as much as we can, now how do we compete? Because if you just took the raw tuning, that wouldn't be a good test, because someone could optimize and do better. On the CQRS version, of course, contention wasn't so much a problem. You get near linear benefit, as I'll show you in a minute, until the number of nodes equals the number of auctions. And when you think about it, that means that every node has exactly one auction on it. Well, then adding more nodes won't help. They're sitting there idle. There are no additional, because that's the granularity of our sharding. So we've now sharded to the point where n equal 1, and nothing gets any better beyond that. However, that's only with a fairly small number of auctions. If you have a very large number of auctions, you have many of them on that node, different story. And tuning is very important. It's very easy to make this perform worse than the CRUD version by simply getting a few tuning. It was sensitive to tuning, is I guess the best way to say it. So, end picture. This is my last graph, I promise. Basically, the yellow line is as we started adding nodes, and we went up to 115 nodes in the end. So nodes is across the bottom here. And how do I write that exactly? The number of requests we handle within that 2-minute period is what I measure going the other way. And what's interesting is that after about the 30 node mark, we actually don't get a whole lot of bang out of adding more nodes to the CRUD version. That's where contention is starting to overcome the advantage of adding additional nodes to the cluster. And the cluster overhead. It's spending all of its time on the gossip protocol as opposed to doing anything else, and this was all using Akka clustering. And it was interesting, these two systems take about the same amount of time to initialize and to bring all of the nodes online. Again, we used exactly the same instances. In fact, the code was just sitting right alongside the other code on the same servers so that we could spin them up easily and test. We would just stop one test, start the next test. Then what you see for the CQRS DDD instance, and this took some tuning to make this work correctly, is a relatively straight line, not quite. It's not exactly 45 degrees. There is some contention. There is a little bit of overhead. As you add each node, there's synchronization. There are things going on with the gossip protocol. The network I/O was quite high, particularly on startup. The load on the database was quite high, again, mostly on startup. Once we stabilized and had all of the auctions in memory, the response time would flatten out, just as you saw on the previous graphs. And we kept going pretty much right up until we had 100 nodes, and we had 100 auctions. So of course now we have essentially one computer dedicated to each auction. And the load balancers are pretty good on AWS, so they were separating the load. Really, the only decision point then was the HTTP node, and there was only one of those in both scenarios, by the way. HTTP was never the limit. The HTTP node would then route that request to the appropriate node, and once that routing table was full, that was a one-to-one correspondence at 100. And there was no benefit at all. In fact, a slight degradation by adding more than 100 nodes. This is exactly what we were expecting to get based on the pattern. So we were most disappointed when we tried it the first time and it looked terrible. And okay, time to start tuning. The tuning is a little sensitive, as I said. Once we got Cassandra tune, once we got Akka tune, once we got the thread pools tune, some network tuning, I believe, on AWS. There's a blog post that describes this in detail. Then we started getting the kind of linear results that we would expect. 100 auctions, of course, is very tiny. This is still a little subset of an example. We would hope that you would be able to increase the volume of each of those graphs without changing their shape that much, by using larger nodes, by using more instances, by having a larger cluster. And I believe that is the template. On GitHub, there is an Activator template that you can go and grab that will have the actual code behind it, that you can see what we wrote. And of course, you can plug your own domain into that and give it a try. It's a good idea. Take a picture of the screen. I usually sit there and try to write it down. Okay, that's my spiel. Anybody, any questions, comments, tomatoes, please?
Yeah, what happens if one of those nodes... Oh, sorry. Yeah, you just demonstrated and didn't talk a lot about this load balancer.
Yes.
But I got the feeling that this load balancer is routing this request for this customer at one node and then is keeping routing that request to that one node because the state is there in memory.
Yes, exactly.
So then I have two questions. What happens if that machine gets full and the load balancer, well, let's get this customer to another machine, and what's going to happen then?
Sure.
And the second question is, how does this graphs differ when I just pull random nodes out?
Okay, when you pull random nodes out, you get this distinctive little dip. And the little dip looks exactly like the startup spike, but smaller. And what I mean by that is what you're seeing, we eventually figured out, was that node fails out of the Akka cluster, therefore that particular cluster shard can't be addressed anymore. Therefore, another node will take over that cluster shard. Yep. And you have to have that configured. This is what I mean by the tuning, being very careful. And as soon as the second node takes over, what you see is an impact to performance while the instances of the actors that represent individual auctions are reactivated. So you're seeing the load time for the event sourcing. And a critical factor, and one of the tuning factors we played with, and you'll see this in the code, is the ability to write snapshots at the right time. And by the right time, the event sourcing and snapshotting in Akka allow you to say, rather than allowing my journal to get infinitely long, if there's a lot of activity on that auction, eventually the journal will get so long that every time I reactivate an instance, it'll be terrible. It'll take 10 minutes to reactivate that instance. Rather than allowing that, what you do is set either on a timing basis or a number of transactions basis, a number of messages basis, I shouldn't use the transactions word, on a number of messages basis, a point to do a snapshot. And then when you restore state, you read the snapshot, then you increment all of the events after that snapshot. By having that snapshot too soon, we affected performance one way, because we spent too much time writing the snapshot. By having the snapshot too late, we made that startup time long. So when a node failed, the dip was deeper and longer. Yes. We'd take longer to start back up. Yep. So that was one of our sensitive tuning. Now to your original question, on top of that, what the HTTP routing node, as it turned out, wasn't the bottleneck for this particular example, but you'd never want just one. You'd obviously want at least two. I'd recommend 3, 4, 5 yep. That are doing the HTTP routing. Now, what that means is that the cluster routing within Akka is also then distributed via the gossip protocol. So there is a cluster leader. It's always the oldest node in the network. But that cluster leader can fail. Yep. There is, again, you get exactly the same characteristic. Yep. You see this little dip. Yep. Nothing fails. None of the requests fail. But you see suddenly response time spike. So number of requests per second go down, depending which way you're looking at the graph. And then you see it recover. And the dip and the recovery are highly sensitive to tuning. That's what I mean by how many HTTP nodes, how large are the messages, does that become the bottleneck? For example, in some situations we have had that happen, where the messages were very large for an Internet of Things customer that we did, that have a wearable device that sends an enormous amount of biometric data. The bottleneck was actually the HTTP actor, because just receiving all of that data was the thing that hurt, and the back-end compute was nothing.
Okay, that's all the tuning you have to do specifically.
That's what I mean by tuning. All of the different characteristics of the model stays the same. We're doing the same thing, but that's what I mean by very sensitive to tuning. Is a tweak to the design means your tuning is probably invalid. And you probably have to go back and start turning knobs again to get the tuning right again.
Okay, thank you.
Measure, don't guess, is my one piece of advice. Please. Sorry, go ahead, please.
Oh, sorry, I have a real question. I'm building such a system right now. And what I have is normally I have views, which are deduced data from your persistent actors. And sometimes new views are created based on actually the data of all persistent actors. So when you create new views in a later release stage, you actually need to load in all these persistent actors into memory to create the view. I don't know if you have experience with this use case.
We sure have.
Large data sets.
Yes. Yeah, it's interesting. Frequently, in situations like this, we'll be asked to write what I would only describe as a secondary view, a secondary materialized view, e.g. a relational database, in addition to the Cassandra store or in the Cassandra store in a separate collection, specifically for the ability to be able to do ad hoc queries and views. And whether you do that as another actor or whether you do it as an external view, like there's another actor listening to this data stream, but all I'm doing is writing it over there in summary format, it is essentially the equivalent of writing snapshots all the time. So you can actually derive that from your snapshots, and that's one technique we've done a couple of times. There is an impact to performance, right? Suddenly you have almost a hybrid system, where you have the traditional relational model and a highly distributed CQRS DDD model. And what we find is that a long and elastic queue between the two of those is one of the critical features, because you have eventual consistency in this model, fairly short. You have eventual consistency of the data warehouse, where eventually is a little bit larger number, right? And that queue, often Kafka, something along those lines, can also be persistent and then be asynchronous to the operation of the system. So the data warehouse does not accurately represent what the exact snapshot of the data in the models are, but it will. And it'll be lagging behind by some value. You can even determine that value and monitor it and have a little graph that says, oh, we're 2 minutes behind, we're 5 minutes behind, we're 20 minutes behind, and then tune for that. It has an impact on performance. Well, like everything. I may as well simply say everything has an impact on performance with a high-end, with a scalable model like this. Does that answer your question, or did I go in another direction?
No, it's more than, this is the traditional case. Existing views need to be updated. But now imagine if you have a new release which introduces a total new view, which actually goes over all the actors. So all of a sudden you need to create of all your state new views. That's, I think, a tremendous impact.
Doing that on a separate cluster is one way we've done it, is start all those up over there on those 3 servers, not your production servers. Because when you think about it, if you read the same journal, you'll get the same answer. So that's the nice part, is that your system is essentially clonable. And you can say, okay, we need to do something nasty, like introduce a new view into the system. That's one of the reasons we often materialize those views, store that snapshot so we don't have to ever do that again. So it becomes a one-off batch job to add that to the system. Adding new message types to a distributed actor system is also something you do very carefully, I guess is the right way to say it. It's something that it's analogous to adding new columns to a database. It's easy enough to add new ones, provided they're not required, and it's hard to take them away. So again, that's a delicate process. Sure, the gentleman down the back there, please.
How would you deploy such a system? So a new version, how would you deploy that? Usually I would use the database, let's say, as an integration point for 2 versions.
Right.
And in this case, I have troubles to
right.
understand how to do that.
Let's say, for example, you added some new feature as opposed to adding some new message type, because that's the easier one. Then, of course, your traditional rolling restart is really the mechanism whereby you apply. What's important is every persistent actor needs to be able to read every version of the journal that preceded it. Right? That's a mouthful, but if you see what I mean, it's just like with messages flowing through the system. If I have an actor X that receives messages A, and then suddenly I start sending it messages B, the persistence of messages A may still exist in the journal. Therefore, I still need to be able to handle A. Even if I turn them into B and then send them to myself, which is one way to go, or I ignore them if that's safe to do, until I am past the snapshot point, where I've now snapshotted my state. Now there are no more A's in the journal. Now I cannot pay attention to A anymore. So it's a careful rolling restart like that with versioning is how you deploy a system like this. Typesafe zone conductor helps with this significantly just in getting it out into the network. But basically you have to stop traffic to the node. It's the traditional drain the node technique where you say no more messages to that node, so I'm leaving the cluster. I turn that node off. I bring it back up. I ensure it's operational, then I go on to the next node, one after the other. Sorry? It's downtime for one point of the cluster, and what happens is as soon as you take it offline, Akka cluster sharding will bring up those instances on another node. So when you bring it back up and you have it operational, it's empty. There's nothing on it yet. Then when you take the next one down, there's an empty server that all that traffic will route to. So there's a little dance that you do that you work your way through the system. It takes some careful DevOps maneuvering to get that right. So.
Different bytecodes running in the same cluster?
Yes, that's possible. Carefully. Yeah, being able to read the same messages, like I said. Typically what will happen is protocols will be stored in one jar file, perhaps. You know, and that jar file has to be versioned one at a time. And you have to be able to read both the current one and the last one. We've often used things like protocol buffer or Avro for that kind of job, because they handle that in the protocol. There are many details, no question. You know, I'm not saying this is simple, but it's not that long a process. Once you see the technique the first couple of times, you start to see patterns. Please.
Have you come across domains that don't shard well? And if your domain doesn't shard, well, can you still do CQRS?
Yes, you can, and you get some magic out of it even if the domain doesn't shard, in the sense that simply separating the read and write paths can help. So even if you have essentially a replicated domain where you can't shard, in the sense you can't distribute the requests by some key, and picking the right shard key is an art unto itself. As anyone who's ever worked with MongoDB can tell you, it's non-trivial to select the correct shard key. Your first guess is probably wrong. And then you kind of think about it for a while and play with it and experiment with it. It's exactly like sharding a database. If you can't find a good shard key, then the CQRS mechanism, CQRS ES can still help in the sense that separating the read and write path reduces your contention by one notch at least. It can't reduce it by n notches, which would be better to distribute it all over the cluster, but at least you're better off than contention on a single source.
Sure.
And some things don't cluster well, no question. But many do. Surprisingly, many do. Anybody else? Are we running out of steam? Just about out of time? Oh, question over here.
What kind of serialization did you use? Like Java serialization, protobuf, or JSON?
Serialization in this case was the default.
Yeah.
We didn't get fancy because there's only one version of it.
Commonly, in production?
Yeah, protobuf is the most common one we see in production. JSON is generally a bad idea, we found, performance-wise. It's a great idea for readability and diagnostics.
Yes.
But generally for performance, we find people go to something like protobuf, Avro, some other, and default serialization is very tricky in terms of rollouts. The binary compatibility between versions is very tricky. So we typically use an integration test to verify that, to make sure you can read not only your current version, but one version back. And that gets problematic with default serialization.
Okay. And then do you have additional tools to, because you cannot analyze the binary?
Again, if the messages are flowing through the system, it's possible to have an actor or a view actor that can subscribe to those messages. Good monitoring helps a lot. And to be honest, in a distributed system, we tend to slip more from logging to monitoring. You know, because watching the flow of messages gives us more information than watching what happened 10 minutes ago. Watching what happened 10 minutes ago, particularly on a distributed log, is tricky because now you have 10 logs or 100 logs and you have to coordinate and see what happened where. So logging, what we find we tend to do is go more with monitoring and less with logging over time. So special tools, to a degree, yes. An emphasis on monitoring.
Okay, thanks.
Mm-hmm.
Quick question. Have
Sure.
you actually benchmarked, Have you tried to benchmark CQRS and ES apart, and then because you get different patterns, you don't have to shard in one case? And then have you benchmarked that? And
Not independently like this. I mean, we've done systems that were just CQRS. We've done systems that are just ES. In fact, we've done a lot of systems that are just ES. And my suspicion is that a lot of the benefit comes from the sharding on the ES side. But the CQRS removes a lot of the contention. So I think the ES adds performance, the CQRS removes contention. Put the two together, it seems to work pretty well. Yeah, the combination ends up quite good. Anybody else? We're good? Thank you very much. Thank you all for coming.